delegates. So I'd like to introduce today's speaker, Dr. Y. Padmavati ma'am. She is presently working at G. Pullareddy College of Pharmacy as a professor and a HOD, Department of Pharmaceutical Analysis, Telangana State. So I would like to give a brief introduction about Madam's biodata. Madam is a recipient of Professor N. Vishwanathan Gold Medal for Academic Credentials in MPharm. She is the head. She was head in the Department of Diploma in Pharmacy for about 3 years, and now she is HOD of Department of Pharmaceutical Analysis. She has teaching experience of about 27 years and guided 57 MPharm students. And Madam is a lifetime member in APTI, IPA. So a book titled Pharmaceutical Inorganic Chemistry textbook, and she is also the member of G. Pullareddy College of Pharmacy Governing Council. Madam has successfully organized at various levels of IPC and APTI conferences. She was also a research person in various national and international conferences as well as workshops. Now, ma'am will deliver a lecture on the topic novel spectral manipulation approaches in spectroscopic methods for analysis of binary and ternary mixtures. With this, I hand over the session to Dr. Y. Padmavati ma'am. Ma'am, please, you may proceed on.
Okay, thank you, Shankar, for your nice introduction. A very good afternoon to you all. A belated Happy Teachers' Day to all the faculty. So I'll start my session with sharing the PPT. One minute.
Yes, ma'am.
I'll start my session. Is this stable? Shivashankar?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay, fine. Today's topic of my presentation is on spectral manipulation approaches and spectrophotometric methods for analysis of binary and ternary mixes. Before I start my talk, so I'll just have a quote to the theme of this eFDP. Theme is best practice in teaching and research. Am I right? Yeah. So one of the best practices in teaching, I feel, is planning. So a solid plan, with a solid plan, you can move effectively in teaching. That's what I feel. And I can say planning and teaching are inseparable friends. A good plan, like daily plan, weekly plan, these are all part of smart teaching. So with this, I'll move to the topic of my presentation. So I guess in today's audience, you have teachers with all specializations, aesthetics, analysis, pharmacology, and all. So I thought I can just introduce analytical techniques. What are different kinds of analytical techniques used? So a bit concepts of spectrophotometric methods. Shivashankar, I can see some audio. It is sounding. So can you please move?
Yes, ma'am. I'll just try. I request all the participants to unmute yourself.
Yeah. Thank you. So, analytical techniques are used for both qualitative and quantitative purpose. So, the two main kinds of methods are used in analysis work, chemical methods and experimental methods.
Surendra Lalwani and Pilchan.
Shiva,
Sir.
mute.
Sir.
Make
Yes, sir.
all questions to be mute.
Yes, sir. I am doing that, sir. All muted. Yes, sir. Ma'am, you may proceed, ma'am. I have muted all the people.
Shiva, madam, your mic is mute. Madam, your mic is muted.
అక్కడికి మేడం దగ్గరికి వెళ్ళి అక్కడ చేసుకోండి.
అందరం పోయినా
Ma'am?
Sir, am I audible? Yeah.
మళ్ళీ mute అవ్వాలి. Ma'am, okay ma'am, you can start.
Shivshankar, am I audible?
Yes ma'am.
Okay, okay, fine. Okay, fine. Thank you. So, started the session with a break. Moving on to, so I'll just introduce what are the analytical techniques which are used in pharmaceutical analysis. So broadly, the different analytical methods are of two types: chemical and instrumental methods. You all know chemical methods are the old ones, but still used in assay of raw materials in wet labs of industries. So the chemical methods include titrometric techniques, gravimetry and gasometry. So coming to the instrumental methods, the main disadvantages, the class of chemical methods are specificity and sensitivity. So to cover that, instrumental methods are used. So here you are using an instrument which acts as an interface between analyst and the analyte. So it gives information about the analyte by measuring some physical parameters. So the instrument methods include separation methods, spectrophotometric methods, and chromatographic methods. In addition to, you have advanced techniques, hyphenated techniques, hyphenation of a separation technique with a detection technique. So I usually use separation techniques in hyphenation or liquid chromatography and gas chromatography. And the detection system, you can use mass, NMR, FTIR. So all even you can couple with two or more detection systems like LC-MS or LC-MS with UV photodiode array like that. So this is all about. So these analytical techniques are used in routine quality control analysis, even for assay of materials research as well as in laboratories. So coming to, so today's topic is manipulation techniques in spectrophotometric methods. So doing spectral manipulation by using mathematical techniques. So I'll just introduce some concepts of spectrophotometric methods before going into the topic. So the spectrophotometric methods are the most widely used techniques. I can say they are well suited techniques because they are simple and economical when compared to your high-end techniques which are expensive, as well as they need a lot of steps starting from preparation of the sample to execution of the results. Right. So the main significance of these spectrophotometric methods will start because the diversity of spectrophotometric methods is considered the most important feature of spectrophotometric analysis. So the fundamental equation which is used in spectrophotometric methods is Beer-Lambert's equation. So the spectrophotometric methods are used for both qualitative and quantitative analysis. So mostly, few techniques are for qualitative analysis like IR spectroscopy and UV visible are used for quantitative analysis. So the fundamental equation for quantitation is Beer-Lambert's equation. You all know about that. So it's a simple relation between concentration and absorbance and also path length. So Beer-Lambert's equation. So here we just have I just gave the different forms of Beer-Lambert's equation. One is with epsilon as a proportionality constant. The other one is with absorptivity. The one more one is with the specific absorbance. So most of the time, being a teachers are we do a mistake. We don't look into what is the proportionality constant used in the equation and what are the units we are using for preparation of sample solution. So that's one kind of error usually we face and will struggle at the end when you do calculations. Right? So usually epsilon is the proportionality constant used when you express C in moles per liter, when you use molar solutions of the sample. Then like that, when you use absorptivity, when you use sample solutions prepared in grams per liter. Like that. The last one is A 1%, 1 centimeter, that is called specific absorbance. The specific absorbance is used when you express concentration in percent. So this notation is the one which is most widely used or used by all pharmacopoeias like IPDP and USP. So the entire quantitative analysis by spectrophotometric method will depend on the selection of concentration ranges for generating a calibration model which is used for calculation of concentrations of unknown samples. So mostly the sources of errors in spectrophotometric methods starts wherein so the inappropriate selection of concentrations will lead to errors. So you all know that Beer-Lambert's law is suitable only for dilute solutions. So moving on to the different types of methods which are used for quantitative analysis, depending on so whether it is one component sample or multi-component sample. So you have to choose the different kinds. So the conventional methods which you follow for single component analysis are use of standard absorptivity value. So the standard absorptivity, the other notation as I said is specific absorbance, A1% 1 centimeter. And this is the method which is used, and we can see in all pharmacopoeias for SF drug substances, right? The next one is the most widely used, suitable for all kinds, is the use of calibration graph method. Then the third one is singular double point standardization. So the first method, use of standard absorptivity value method, is applicable right now when you know that constant value. And this is the method which is suitable when you don't have pure form of the sample. That's the reference standard is not available, or it is very expensive to spare even microgram quantities. Right. The next one is calibration graph. So here you need an external standard, so which should be a reference one. So you'll be preparing a calibration curve, from that you'll be calculating it. This is very commonly used method. So when you can generate the best fit line for calibration, it is a very accurate method. Then single and double point standardization. So the single point, here just you are comparing the sample concentration, the sample absorbance with the standard, so single standard. So this method, simple equation I'll say, remember, I just want to come in track to manipulation methods. If I explain these, it will be good, you'll be reaching that. A1 by A2 is equal to C1 by C2, or C1 by C2 is equal to A1 by A2. So you're just comparing the absorbance values with that of a standard, and you're calculating the concentration. So this is very applicable when you have a very good relation between absorbance and concentration. So that relation should be linear and proportional. So you see the difference. So linear, and Beer's law always know. So the concentration, if you increase linearly, right, or proportionally, there should be an increase in absorbance. So there you use the double point standardization. So the relation is linear. I mean, the relation between concentration and absorbance is linear, but not proportional. Then you are just bracketing with the two standards. One standard concentration is less than the sample, the other standard concentration is more than the sample. So these are all the simple three methods which are used for single component analysis. When it comes to multi-component analysis, so you have different methods. So you can just treat it the sample meter as a single component by selecting a wavelength at which all other components does not show any absorbance. Then you can go ahead. So the other one is using absorbance corrected for interference. So in this method, you can act for a method for that interference. You can calculate the quantity or concentration of that, and you can correct you can correct responsible for that interference, and you can go ahead it as a single component analysis. The other methods are simultaneous equation method, absorbance ratio method, derivative and difference spectrophotometry method. So these are all the ones which you can simultaneously estimate the 2 or 3 components which are present. If it is a derivative and different spectrophotometric methods, you can go for even up to 4 components which are present in the sample. So the main requirement for any kind of multi-component analysis is it has to satisfy the 2 conditions. The first one is because it's a multi-component analysis, simultaneously you are doing. The first one is the total absorbance which is obtained from the sample mixture. It should be total of the absorbance of individual components. Right? Suppose if capital A is the mixture sample, sample mixture absorbance A1 plus A2, and 2 are the components. Right? That condition. One more thing, when it comes to simultaneous equation, if you select 2 wavelengths for determination, each component should show absorbance at lambda max of each. That's one. Then coming to absorbance ratio method, here you are making use of a point, this is a wavelength which is called isospecific wavelength, where the 2 components will show same absorbance. So you are just calculating Q values. The other name for this method is Q value method. So Q value is nothing but you are taking the ratio of absorbance values of any component at 2 wavelengths. So out of the 2 wavelengths, one is other is lambda max of either component, right? You can take lambda max of 1 or 2. So that is absorbance ratio method or Q value. So you have the other techniques called different derivative and different spectrophotometric method. So derivative spectrophotometry is a well-suitable technique when you need spectral resolution. When the compound is not having well-defined characteristic absorption at the defined wavelength range, then you can go for resolution of those spectral characteristics by using derivative. Moreover, this is also the one which can be used. You can go for first, second, and fourth up to fourth derivative for analysis of multi-component samples. Then coming to the different spectrophotometric method, the word itself indicates you have certain molecules which can be ionized if they get changed. If you change the pH, you have some molecules whose functional groups will get ionized to get different form when you change the solvent or when you change the pH of the solvent. So then by changing the pH, right, by changing the solvent system, you can bring about the changes in spectral characteristics of the molecule, right? That will result in difference in absorbances. There comes the elimination of interferences, because the interfering molecule can't undergo the same procedure which the molecule of interest is undergoing at the defined conditions, right? That's another beautiful technique for analysis of, but it is specific. So the conditions apply for applying the different spectrophotometric methods. So these are all the methods, right? With this, I can't say spectrophotometric methods can be used for all kinds of samples without prior separation, without any interference in measurement, right? So there comes definitely you have to consider sometimes, they have their sensitivity issues, the reproducibility issues may not be right now, so applicable for all conditions. All these methods, if you take simultaneous, if you take absorbance or derivative and different spectrophotometry methods, conditions apply. So first we'll be giving these conditions, then we'll check whether the particular sample will fulfilling the conditions, set conditions, then we'll go further. Yeah, so coming to the topic, spectral manipulation approaches. So you are just manipulating the spectral characteristics by using simple mathematical techniques, simple transformation, derivative. You are just converting to a derivative, subtraction, division, right, addition, multiplication. So sometimes you will be adding, adding and again dividing. Sometimes you are subtracting and again multiplying. So all these techniques are applied for changing the spectral characteristics in such a way that you can nullify the what you say, the effect of interference in the spectrum, right? The effect of the absorption, which whatever you can see in the methods. So these spectral manipulation approaches, they'll make use of these, like you can say, the basis are some cases I can use parameters, right? So dual wavelength, absorptivity points, area under curve. So you can make use of a derivative spectra, subtraction of the amplitudes of the ratio spectra. So you can calculate the amplitude difference of ratio spectra, or you can compute the geometrical representation of amplitudes of ratio spectra. So before starting, let me say, this is the afternoon session, so peak after post-lunch session. So my topic is like a bit oriented with mathematical transformations. I'll try my best to reach you, right? Because this is virtual presentation. If it is physical, I can make use of something blackboard or with my. So this one I can explain you so more clearly rather than. Even now I can't see my expressions also. For you the video is visible, for me it's not, right? So anyhow, I'll try my best. So going ahead. So now I'll just list out, don't scared of the list of methods, thinking that she's going to explain all this, maybe around 6 she'll be leaving us. Oh, not at all. 6 or 5. Very difficult to cover whatever the techniques I'm going to list out in this session of 1 hour. So absolutely, it's very difficult. But I'll just do an attempt to reach you in giving you the concept right now, such that you can attempt in doing. If I explain about 2 techniques, the other techniques you can try on your own, looking into the data, right? Okay. So this is first I said, no, dual wavelength modes. So you have some methods, that is the manipulation approaches based on manipulating the zero order absorption spectra of the compound. Usually in conventional methods, I said, no, simultaneous or Q-value method, you'll be selecting 2 wavelengths, right? So meeting some certain conditions, you'll be like that. In all these methods said, so these are the list of methods by selecting 2 wavelengths, right? So you are doing some spectral manipulation. Excuse me. You are doing some spectral manipulation, and you can apply the methods for samples like binary mixtures and tensor mixtures. Coming to, so the first 2 are, I'm going to explain the highlighted ones. The induced dual wavelength method and dual wavelength resolution technique. In addition, you have all these. I just listed out, have a glance at, or please make a note. Anyhow, no need of noting. You have a recorded version in YouTube, I guess, Shivashankar. So absorption factor method, absorbance subtraction method. See all this, this here itself you can say. Simple manipulation techniques are used for resolution of the spectra, for getting better spectral characteristics, or for minimizing and eliminating the interferences. Like you have area under this method, you might have, I can see. So one more thing I want to say before starting. So you can just Google it, or in PubMed, or in right now Science Direct. All the papers are paid ones for this. So now if you become expert working on these techniques, but it's not that easy. It's you have a very good publications, right? If you start working your research with these methods, it's a good suggestion. Simple UV spectrophotometric methods are available in each and every college now. Everybody are going with the advanced instruments. So rather than buying 2 or 3, one advanced instrument will serve all, right? Okay. Yeah, so I'll explain about most of our national journals. You can find this area under curve method. So then in that also you have area under curve correction method, ACCM method. You can also have compensated area under curve method, and spectrum subtraction. I'll just list out the methods first, then I'll go with one after the other in detail. So the next one based on absorptivity value. So absorptivity point here I can say it's isoabsorptivity point, right? So three methods you can formulate: absorbance subtraction, advanced absorbance subtraction, absorptivity factor spectrophotometric method. This is also known as it's not small a alpha factor method. So the next ones are these are the methods which are based on calculating area under the curve. Right? Most of the time the spectrophotometric methods are based on measuring absorbance. Am I right? Here instead of absorbance, you are just setting 2 points, wavelength points, and you are mathematically calculating the area under the curve and calculating the concentrations, right? Yeah, so all these three methods which I already listed out in dual wave. So based on derivative. So once, if you feel like the spectra all the time, it's not that you'll get a well-characterized Gaussian shape peak or bell-shaped peak in the absorption spectrum, whether it is UV region or visible region. So most of the time they may be very broad. That's the main drawback. That's the reason they can't be used for qualitative analysis, for characterization of the compounds. So this broad spectrum, sometimes it's difficult to point out what is the exact wavelength at which this particular component is showing the absorption maximum. Right, there comes into the picture of just a transformation of your zero order spectrum to derivative spectrum, right? So these are some manipulations which you can work on derivative spectra. So amplitude subtraction, modified amplitude subtraction. So by calculating amplitude factor, so you can summate the amplitudes of the curve at 2 different points. You can also simultaneously take the derivative ratio, then differential dual method. There it's just a dual method. If you just transform to derivative spectra here also, you can perform the same method, differential derivative ratio, then derivative transformation. These are some techniques. So not much. So amplitude subtraction. These are all so to look into so how we can transform. Then based on these, we'll be moving to the other methods. So this is methods based on subtraction of amplitudes of ratio spectra. So you all know what is an amplitude in spectroscopy, right? The height of the vector, the height of the wave is known as amplitude. So for our spectrophotometric methods, for calculation, when you do practical, if you set 2 wavelengths, I can say one starting at the minima, the other reaching the maxima, that's a peak. So starting point, one wavelength point you can take, and the peak maxima you can take as the other wavelength point. Then if you just look into the in-between, that will give you the height of your wave or the peak which is there in the spectrum, right? So out of you have so these are you can see a very good number of publications worked out on this technique. So ratio subtraction method, successive ratio subtraction, extended ratio subtraction method, simultaneous ratio subtraction method. So these are all the ones which are very much used for analysis of the samples. Analysis of drug molecules, even in presence of degraded products, right? They're degradation products. So I can say usually HPLC is the technique which is used for developing stability indicating. Even by using these spectral manipulation approaches, you can develop right the stability indicating methods for analysis of drug molecules in presence of their degradants. So the other one is there is the ratio amplitudes. Here it is the difference, right? So you are taking amplitude difference of ratio spectra. So the ratio spectra is nothing but it's a spectrum constructed between concentration and the ratio of the amplitudes of the different addition and subtraction. We are just doing the computed geometrical representation. So you are just converting in the, you are just adding some amounts and calculating back, then subtracting, so divising. So all that will be. So mostly you, I can see good number of papers even on ratio H point standard addition method, right? So, but I may not be. So I'll cover the 4-5 important methods. So moving on to right, so one by one, what can I do? So don't scared looking into the data which I just dumped because these are all mathematical. You have a mathematical theory for each method, then the same one you can execute very easily. It's not that difficult which you read the theory. It's very simple. You can do manipulation of the data in a software, right? So, but no, if the mathematical derivations, how the manipulation is done. So to nullify or to minimize the interfering compounds. The first method is induced dual wavelength method. So already I discussed, right? The dual wavelength methods, simultaneous or absorbance ratio method, that's a Q-value method. So there, the condition. So you are doing this. So you are taking two wavelength, right? So if always for all these methods, I'll be explaining the concept of the manipulation by taking example as a binary mixture consisting of X and Y components. So always I'll consider, when I'm talking about the determination of X, I'll consider Y as an interfering component. Obviously, no. So other than that, most of the time, in very few formulations or in very few samples, you can expect the interference of excipients or other components present. So mainly all these spectrophotometric methods component when you are measuring. So I'll just use the binary mixture consisting of X and Y. When I talk about determination of X, Y will be the interfering substance, right? So this commonly the dual wavelength method, the conventional dual wavelength method is based on the condition that, so the absorbance of the interfering compound, I can say Y I'll consider as interfering component at the two wavelengths, and if you calculate the difference in absorbance, and simple I can say that thing will be showing same absorbance on two wavelengths. So then it's easy, right? You can calculate. If it is 0, no, it's the same. When you can calculate and subtract, then the dual wavelength method is successful. But so induced dual wavelength method, this is with a slight manipulation of spectral data. So the condition is when the difference absorbance of the interfering substance does not equal to 0, right? So the basis for this method is you have to select the two wavelength, right, where the interfering component shows different absorbance values. Then only you can apply. So you always remember. So I can't say that all these techniques can randomly apply to all kinds of samples. No. First thing, whenever you start, you want to design or you want to develop a spectrophotometric for analysis of multi-component samples, the first thing you have to go ahead is you have to check the solvent, right? So then you have to select the solvent in which it is having good absorbance. If it has good solubility, that reflects the absorbance. Once if you select the solvent, then you have to check how long it is stable. Does it stable that both the analyte molecules are stable in the solvent selected? If they are stable, how long? That data can keep. Then you just generate the absorption spectra of all the individual compounds. Suppose you have X, Y, Z in the sample or X, Y. So you take the pure samples of X, pure sample of Y, then you generate absorption spectra. Now the next one, if it is multi-component, if it is simultaneous, then you just overlay the spectra of the two components and you check how how the overlay spectrum is, whether the two absorption spectra are completely overlaid, right, partially overlaid, or severely overlaid. That comes. It is very much. I can say now that dual wavelength, all the dual wavelength methods are applicable only when, right? So you should have a very good overlay of the two. Then only you can define the spectral characteristics, right? That's what. Then looking into that, then I said some conditions, no? The dual wavelength, the difference should be 0. Here, if you want to apply induced dual wavelength, so that interference substance does not, the difference should not be equal to 0. So that is the basis for this method. So usually this is very easy and we'll get very good results. You can apply even for the laboratory prepared sample mixtures or pharmaceutical dosage forms, what, right? So here coming to the other in the coming slides, the advanced methods, you don't require any division or multiplication, or you are not calculating any ratio or not that. So here I just gave only for this or one more I gave. So here what you are doing is, I said the Y component is an interfering substance. Definitely that's showing interference when you calculate X. So because the difference is not equal to 0, what you have to do is, you have to cancel the absorbance of this Y component when you are measuring X. So that can be done in this method by calculation of equality factor, which is represented as Fy, equality factor. So equality factor, it's not it's a simple mathematics, you just try to follow, it's nothing. So equality factor is nothing but you are just taking the ratio of absorbance of Y component at the two wavelengths, capital A Y1, capital A Y2. So absorbance of Y component at first wavelength and absorbance of Y component at the second. So you are selecting two wavelengths, right, in such a way that the absorbance of Y component is different at those two wavelengths. That's the condition. So I just gave an equation. I put it right when explained in the introduction. The fundamental condition to be fulfilled for analysis of multi-component samples by spectrophotometry is the absorbance of sample mixture is equivalent to the sum of absorbance of the individual, absorbance of the all the components which are present. So I just gave you can see capital A1 is equal to AX1 plus AY1 and lambda 1. So Y suffix is lambda 1 first wavelength, 2 suffix is for the second wavelength. So now the capital A1 represents absorbance of the mixture at lambda 1, capital A2 is the absorbance of mixture at. So I'm just you can see then Fy is calculated, which is the equality factor. You try to, if not leave it, then I can go with practical implementation. Then first I'm multiplying the equation 1, then multiplying the equation 2 by Fy. So then you can see that. So now what I am doing is I want to see, I said no, the difference in absorbance contributed by Y component is not equal to 2, is not equal to 0. So what I am doing, I am just tracing out by doing this spectral manipulation. So this is theoretically. So in instrument, it's a different. So I am just calculating the absorbance contributed by this Y, right, and just component, right, is get cancelled. Now whatever this 5 equation will indicate that whatever I just saying that I just assumed Y as an interfering component only to calculate X. Now I am doing the reverse procedure, right? Not reverse, the vice versa. Now I am calculating equality factor for X, and then I am calculating the interference of X, right? So for calculation of Y. So here you have to use two separate procedures, the same procedure for determination of the two individual components. So this is a simple method. You can apply for all kinds of binary measures. So I just gave an example which they did analysis of hydrocortisone acetate and fusidic acid in a topical cream formulation in presence of methyl paraben and propyl comfortably without interference of you can see that MP is methyl paraben, the spectral. They here you can see a good overlay of the four components: fusidic acid, hydrocortisone acetate, methyl paraben, and propyl paraben. So if you look into the spectra of methyl paraben and propyl paraben, the pink dotted lines and the blue dotted lines, you have a very good spectra, right? You have very good absorption characteristics. So definitely they'll have interference, right? So but by using this method comfortably right now, so you can eliminate interference and you can get exclusively the concentration of X when you calculate equality factor of Y and cancel it, right? What you are going to cancel? The adjorbance of Y by calculating equality factor. So in the similar way, you can do for that. So this is an example. So the next one is the same kind, dual wavelength resolution technique. So this is also used. The basic condition for dual wavelength methods, as I said, you should have a good complete overlay of the spectra. So it's not partial. So you should have a complete overlay of the, it's not superimposing. So you should have a very good, at least at the 3-4 points, you should have a overlay of your, the spectra of the two compounds. Then it's good to select this kind of methods. Here, in the dual wavelength method, I said no. Right. So first you are calculating for X component and the second you are calculating for Y component. So here what you are doing is you are using a simple manipulation technique for resolution of the spectral behavior, right? You are constructing a calibration curve of pure X right now. So like in the case of a dual wavelength method, between the difference absorbance and X, and you'll be calculating Cx, right? So now in right now, what is it? Practically when you do this, you are just what does it indicate? If you can generate a regression equation, means that indicates that whatever the spectral data you obtain from this method, it's purely because of one compound, I can say, right? Yeah. So from this data, so after doing this induced dual wavelength calculation, you can generate zero order spectrum of X from the sample mixture. So see that sample mixture consists of both X and Y. I just cancelled the adsorbance effect of Y by using equality factor. Then I generated absorption spectra of series of concentrations of the sample mixture, considering as whatever the absorbance you got is only because of X, right? So that's done. So in this dual wavelength resolution method, you are just calculating. Now you have to, if it is the induced dual wavelength method, what you did? So next time you considered X as interference and you did. But here you need not know that. Just you can do in spectral manipulation. You can get the zero order spectra of Y by just subtracting spectrum of sample mixture minus spectrum of X, right? So this all you are doing for sample mixture, you remember, right? Then it's very easy. Now you will get the zero order spectrum of Y. You can note down the lambda max. Then you can prepare a series of concentrations and determine, and you can determine the unknown concentration of your sample mixture, unknown concentration of Y component in the sample mixture from this equation. So this is another method, so which can be used. the same example. So whatever he gave, even the others, they published three spectral manipulation methods. So one is induced gale wavelength, the other one. The next one, they just subtraction method based on absorptivity values they did 3. Okay. Hope even I can't see anybody. I'm just moving up. If any doubts, or if you want me repeat, or if you want me go a bit slow also, so you can stop me, right? I can repeat. It's a condition. If anybody are interested in to listen, exactly. If anybody want to work out on these methods, very much appreciated. Okay. So the next one is methods based on absorptivity points. You might have, you all may be knowing isospecific point. You might have heard about that, right? Isos. It's not isobestic point most of the time. Even me, when I joined in the initial career of my teaching, so if I see my so those preparation class notes, no, I wrote it as a isobestic point. Some of the books also, but later I corrected. It is isospecific point. So it's also known as isoabsorptivity point, right? So isospecific point is nothing but the wavelength where the two components of same concentration will show same absorbance and absorption. You all know absorptivity is calculated based on absorbance and concentration of sample. If the concentration of the sample is same, obviously the absorptivity value is same. So you are making use of this isospecific point. Remember, the isospecific point is the wavelength at which the two components will show. The two components in the mixture will show the same absorptivity value. Here, no, so yeah, so at this isoabsorptivity, if you just intersect the spectra of two components, you have some crossing over points. It's practically, it's very easy to remember, right? So the crossing over points of the overlaid spectra, the intersection point of the two spectra is also known as absorptivity point, right? So at this, if you just measure, if you take this wavelength and measure the sample mixture absorbance, that is right now, it's uniform at any two wavelengths if you take, if it is of the same concentration. So usually this absorptivity method, what you are doing is you are just calculating the total concentration of X and Y at this point. Then we are just correcting this simple scanning UV visible spectrophotometer of make Shimaju, so which has a UV probe as a software. In that we have all this inbuilt manipulation techniques. We did that. Even besides that, you have the exclusive softwares for. Suppose if you apply this method for analysis of mixture of two drugs, so having a very good overlaid spectra intersecting at types of the point, the condition to update, right? So Y is extended over X, but X does not show contribution at the other. It's not. So what can I? If you take the two absorption spectra, so they are intersecting. They are overlaid spectra, but the intersection and overlay is such a way that the Y component spectra is overlaying with X, but the X, the starting beginning point of X spectra is just overlaying with the tail portion of the, I can say, I should not use tail, this is a terminology used in HPLC, the end portion of the spectra of X component, right? So only at one wavelength the X component is showing the absorbance, right? That is at intersection point. At other wavelength, it's not showing. So usually you'll be selecting two wavelengths in this method. One is isoabsorptive point, the other one is lambda max of the one of the component. Because if the X is not showing, you can take the lambda max of the other component. Similarly, so by using a simple manipulation step, I can, so don't get scared, I just put as it is because I don't have time to generate these mathematical equations. We can do it in Google, we have some softwares. So just you have to calculate a absorbance factor, right? So the absorbance factor is calculated for Y component, right? So you see, Y is having absorbance at isospecific point as well as its absorption maximum. But X component is having absorbance, is showing absorbance only at isospecific. It's not showing because it is not get, the spectra of X is not get extended to Y, right? Yeah. So these are the simple equations. So I should not say that simple. So you're just calculating, see my cursor. So you're just calculating the absorbance factor. That's a simple ratio. Like how you calculate Q value in the Q absorbance method, right? So like that you are calculating the absorbance one. Then by just substituting in these two equations, we can get the concentrations of X. Yeah, so one example I gave, he just analyzed the 3 samples, chloramphenicol, dexamethasone, sodium phosphate, and also tetrazolene hydrochloride in presence of benzyl alcoholic chloride as a pressure weight. Right? So we just used this absorptive subtraction method for calculation. So for determination of chloramphenicol and dexamethasone, he used 257. We can see this is the dotted blue line one is for dexamethasone and the solid black color one is for chloramphenicol. So you can see now cursor. This is the crossing over point for these two components. You can see only here. Now the point whatever explained. Let us dexamethasone is Y. Chloramphenicol is Y. Dexamethasone is X. So the X dotted line, the spectrum is not get extended to complete overlay of this one, right? So you can see, yeah, here. So the other point you don't have. Here one more crossing this at the lambda max or at the extended point to the end of the spectrum, you don't have any crossing over point. So he worked, so he is a scientist, IM Watt T, F is silent. He did a lot of work on manipulation methods. So if you just Google it, you can find n number of. So most of them are paid versions, the articles. Most of the advanced manipulation methods are by him and his co-workers. So he did all the 3 or 4 methods I didn't mention with this manipulation technique, which involves considering isoabsorptive point. So the next one is methods based on area under curve. So this method is applicable. You can apply this method. As I said, dual wavelength, the absorptivity, those two methods based on those 2 parameters, they should have a complete overlay or overlap. Right? So when the 2 equation method, AUC method, so even it's like now 10 years back. I read an article when I'm new to research 10 or 15 years back. So what is this AUC? So usually area under curve is a terminology which you use in kinetics, right? So how come you use in spectrophotometry? I thought that time. So right, these are the methods you have from that time. Now the researchers started working on that, on these manipulation approaches, because they're very comfortable. You don't need any separation technique. Even the reproducibility is good with the very good accuracy and precision, right? they started working on publishing, right? So that time also it is there. Then I thought, what is AUC? This is area under curve. So when this method, as I said, when the two spectra are partially overlaid, and also when the spectra is not well characterized, right? You don't have the exact Gaussian shape peak, or you might have a very broad peak where you cannot exactly determine the lambda max for determination of concentrations, right? So this method is very good whenever you have such kind of spectrum. So this is a simple calculation area under curve. Here what you are doing is you are just selecting 2 points on the spectrum. So I can see because it's very easy. This is a overlay. You can see now they are partially overlay. This is Santhiram and domperidone sample. You can see the overlay spectrum, dotted line and the solid line. Even the spectra is not good. One is you can see always the spectra should start with a minimum, should reach the maximum, the peak. Sorry, start from the minimum, should reach maximum, and then it has to come down to minimum. Only those kind of peaks are considered for noting down the lambda max values or for determining the sensitivity. So when you take any sample of concentration X, right, the adsorbance value may be low, but you have a greater area under curve values, which are more comfortable. In this way, even for the low concentrations where you don't get measurable adsorbance values, you can get the areas. So in those conditions, you can say whenever you want to go for a sensitive method, you can select area under curve correction. So this is the example I just gave. So the next I already told, no? So applied derivative spectra. Whenever your spectra is it's not good like just with Santhiram and domperidone. So you can go for a derivative. You'll get well characterized, well defined so peaks where you can see absorption maximum. Then next, Shiva Shankar, how long I can extend?
Yeah, ma'am, you can continue.
Yeah, few more. And maybe another 20 minutes it may take, okay?
Yeah, sure, ma'am.
As I said, no. So now the manipulations and derivative spectra, they are widely used, mentioned already for developing stability indicating methods, right? So you can determine the drug component in presence of its ingredients. So in these mostly widely used methods are by calculating the ratio of amplitudes and are the differences between amplitude ratios at two wavelengths for one component, right? So these are most widely used. If you just look into the recent publications, most of them are based on manipulation of the amplitudes of the spectra, right? Usually they are suitable for both binary and ternary mixtures. Here the basis for this thing is you are just nullifying or you are minimizing the or eliminating the interference of compound by dividing the ratio spectrum with standard spectra of one of the analyte as a division. I'll just show in that so UV probe. It will be easy. If I speak, may not be. So this is the most widely used method, ratio. So these three methods, the ratio absorbance difference method, RAD, first derivative ratio spectra method, and extended ratio subtraction method. So these three are the methods we worked on it last year. So one of my student, Jafar, so really he worked. He started with with a review article on this manipulation methods, but of course we could not publish that. But no, we did so good research work for analysis of fixed dose formulation of antidiabetic drugs. Metformin, glimepiride, ibuprofen. So all the 3 drugs. So we applied these methods for binary mixtures, of course. So I'll just here a simple thing, few points I'll explain. Excuse me for just web capturing the content, because I don't have time to type the mathematical equations. Excuse me for that. The simple fundamental equation for all multi-component analysis by spectrophotometry is the sample mixture absorbance is equivalent to absorbance of individual components. So you know B Lambert is capital A is equal to small a BC. B is always path length 1 centimeter. I can also write the same equation like this. Absorbance of sample mixture is equal to absorptivity of X, concentration of X, same. So this is nothing but absorbance of X component, absorbance of Y component. So what I am doing now here is, now I am dividing just for getting a ratio absorbance with a standard solution of X component, any concentration, right? So you can see, so Cx0, right, exponential. So I'm just dividing it. Then you will get a ratio Cx by C0, you can see. Cx is the concentration of X component in the sample mixture, where C dotted X is the concentration of X, which I used as a standard solution for getting the ratio. Got it? So now here the Cx by C0 is a ratio constant. So if I eliminate this ratio, I can eliminate, I can remove the interference of X component. So for that, what I am doing now, I am just taking the difference in the method. Ratio I calculated, now I had to take the difference in this absorbance ratio at the 2 wavelengths. This is one equation. The same I can generate another equation, because for all these multi-component methods, I'll be taking 2 wavelengths. Don't forget that condition, right? So 2 wavelengths are selected. They may be lambda max of each component. They may be one is lambda max, the other one is isoabsorptivity point. Like that you can select. Now, if I just this is, yeah. Now I'm just taking the difference between the 2 ratios which are calculated lambda 1. So the AM0x at lambda 1 minus. So now I'll be getting the same. So can you see anywhere here? Are you getting? Yeah, the same one. So you don't have here the absorbance exclusively with Y. So can you see? AX is, you can't see anywhere in the equation when you take the difference of ratios measured at 2 wavelengths, right? So this is all only the absorbance of mixture and absorbance of Y. So I just eliminated by taking this constant out, by taking the difference of absorbance ratios measured at 2 wavelengths, right? So this is the main basis for this method. So I'll just show you the data which we did, then it will be easy to refer. The next is first derivative ratio method, the same one. So after removing the constant, if you just derivatize that, you'll get more resolved spectra. So you are in a right now confusion that whether it is calculated exactly. Can I eliminate this Cx by C0? So then that can be ruled out in this method. Directly, it is transform your conventional zero order spectra to derivative, and if you do the ratio, or first you take the ratio spectra, then convert into derivative. Automatically, in the derivative mode, the Cx by C0 gets cancelled.
Question, sir?
Right now, you can directly determine the Y concentration. In the same way, you can generate the same kind of equation by considering Y as a constant, saying that Cy by Cy naught u, right? So this is another method where you can eliminate. The next is extended ratio subtraction method. So this method is based on the first derivative, what you say, ratio absorbance method, RAD method. First the ratio subtraction method. This one is based on the ratio absorbance method. For that we are just doing some manipulations of you are dividing the ratio absorption spectra with a divisor, then you will get constant. That constant is eliminated from the spectral data, then again multiplying with the division. Simply I'll say, now I have a formulation with X and Y in combination. The sample mixture consists of X and Y. I want to calculate the X concentration by this extended ratio subtraction method. So what I am doing is, after generation of the now I have to first generate the ratio spectra. For that I am just dividing with always remember, if you want to determine X component, you use concentration of Y as a division. If you want to determine Y concentration, you use concentration of X as a division, right? So this is how you will be doing, and the spectral manipulation will give you this will be the mathematical transformations. Okay, so these are all the 4 methods which I thought of explaining you. The others I didn't find much of. You have publications, but most of them, these are very good, bit complicated methods when compared to the ones, all others are simple subtraction and addition. So I'll just want to show you the research work data which we did last year for analysis of the anti-diabetic drugs in fixed dose populations. So we just developed all these 3 methods: ratio absorbance difference method, extended ratio method, and ratio spectra method, that's a DD1, for estimation of metformin, glimepiride, and one combination. The other one is metformin hydrochloride and glimepiride. And bulk, both the pure drugs and even formulations, we tried these. Now we just this 2 formulations we did. I'll just take time to explain one. Maybe already got bored of this mathematical transformations. So just if you take ratio absorbance difference method, these are the steps. The first thing is, you have to, as I said already, for any kind of analytical work, check solubility, check solvent stability, then determine lambda max, then overlay the spectra. The same when we did, we measured the lambda max, then divisor concentration we had to. In all these methods, you are using a divisor for generating the ratio, then you are using a subtraction technique for removing the constant which is obtained, then determination of analyte concentration, the same way. So I just the 3 methods. The first one is ratio absorbance difference, RAD. The second one is derivative ratio method. The third one is extended ratio subtraction method. I'll just show the graphs, then it will be easy to you to graph. So the first thing is, we will be doing trials for what is the concentration can I use for doing the division, to use as a division. So that I'll try, right? Then I'll generate a ratio spectra. After that, we can eliminate the constant. Then for calculation of amplitude, because this is the amplitude ratio method, right? Most of the time, the derivative, if I use the word in derivative spectra, you will not be getting the absorbance. So most of the time, amplitude values are displayed in positive and negative values, right? So that's the reason whenever you transform to a derivative, I'll be using the word amplitude instead of the absorbance. So then lastly, determination of analytical concentrations. So this is just a trial for mixture. You can see we use started with 2 micrograms as a divisor. This is metformin and glimepiride. So for analysis of glimepiride, I used metformin as a divisor. As I said, for analysis of metformin, I used glimepiride as a divisor. So you can see. Then now next point I said no, I had to select the 2 wavelengths for calculation of amplitude. So usually amplitude is height of the wave vector. Here I can say height of the peak. So how I'll get height? If I take the trough wavelength and peak wavelength, then I'll get the amplitude. Suppose for this peak, you can see, can you see the cursor? Yeah. So this peak is 224 and the trough is at 244. If I calculate, if I use this, if I just calculate the difference, then that will give you the amplitude, right? So I am selected. The next step is I have to select the wavelengths of trough and peak for analysis of this. So now first I took the sample mixture, I took absorption spectra, then I used divisor accordingly, then I got the ratio spectra. From the ratio spectra, I select, right now, we can select the trough and peak max. So now next, right. Okay. So this is all about. Now, if you just do all this, now you can get a series of spectra like this, and this is a lambda max, I can say. You can increase the concentrations. First I took 2 microgram per ml of metformin glimepiride with a divisor of 2 microgram of glimepiride. So the first one for determination of metformin. Then the next series of concentrations we used 4, 6, 8 and 10, right? So from the spectral data I can just develop calibration model by taking the absorbance ratio, so which is displayed as absorbance in the instrument. So like that we can do derivative spectral method, right? So I just transform. Here I need not cancel the concentration on spectral manipulation. So just I took this one by the first derivative. So all these are for different concentrations. So then after getting the first derivative spectra, then I took ratio spectra by using divisor, the same concept again. So I just converted into ratio. We did transformed the conventional first derivative spectra to ratio derivative. So this is the ratio derivative spectra. Now I have to select the same procedure, trough and calibration model. So the third method is extended ratio spectral method. So just extended ratio subtraction method. So you are just extending. You can see here a plateau region. See all the spectra. So this is 2 micrograms, 4, 6, 8 and 10. You can see the cursor. Then so you can see the plateau region. This is called constant. This is constant. So this is constant what we generated, Cx divided by C0x. You remember, theoretically in theory calculations I just subtracted that. So in spectral manipulation in the software also we can just subtract and we can get spectra like this. Sorry. Yeah, so after removing this, the center one will be the, after subtraction, you can see this is supposed to be the first. So this is one. I just removed the, I can say, the constant, the ratio of the constant ratio is subtracted from this extended overlay spectra. So now it's very easy. You can select this lambda max, right? This is sample mixture. Then you can generate with the pure drug sample, the calibration model. Then you can calculate the concentration of the sample mixture without the interference of. So you can determine glimepiride without interference of metformin and vice versa, right? So this is all about. So I tried my best to reach you. I'll just show the software which we all use in UV spectrophotometers. If it is a SHIMAD, you make the UV probe, right? There you have the manipulation approaches option. I'll just show how you can do if you are patient enough. Otherwise, what is the Shivashankar? Shall I?
Yes, ma'am. Yes, ma'am.
I'll just one more minute or two. Okay. Is it visible?
Yes, ma'am.
Yeah. So you can see this is a UV probe software. I mean, you have three different modes in this. Usually, you have spectrum mode, photometric mode. Even you have multi-component analysis and kinetics, right? So I'm now using the spectrum mode where I have loaded the previously worked samples. So I just took 4 microgram per ml metformin and glimepiride, right? So I had to take raw data. So this is all I just worked on. So I just clicked on that. Now you can see before that, let me start from here. I thought of conventional. Yeah, now I'll file, open. Yeah, one more desktop. So I can take 4 microgram per ml. Okay. Oh, again it went into, so no problems. You can see the, if I highlight or even in operations, you can see data point, manipulate, peak, point peak area, swing box. So you can see by selecting these options, you can peak, you all know that for picking the lambda max, manipulation. So you can do all here the mathematical manipulations which I discussed, the different manipulation approaches, right? So peak area under curve, no? So that also you can execute as a manipulation of spectral data. So if I just click this, then this manipulate window will be opened. So in this, you can see all. These are the different manipulation modes. You have arithmetic, blanks, subtract. Sometimes if you prepare reagent blanks or the other kind of blanks where you have, you have some, right now you cannot process them until they don't interfere with the absorbance. But sometimes they'll give absorbance, you may need to correct it. Then we can go with this mode, data set, which we are going to use, like interpolation, normalization, transformation. You have these options. I'll just take data set. Then I selected this file, right? Now the sample solution, which consists of this. Then I'm just, I said no, this raw spectral data, spectrum of this combination, should be divided with a divisor of any concentration. Now that any concentration, how you select that concentration is by trial and error until you will get a very good ratio for construction of the calibration curve. I'm just selecting. You can see in the operation, I can select a division, right? Then what you are using for a division? I said for determination of glimepiride, I had to use metformin as a division. The solution of metformin as a division. If I want to determine metformin concentration from the sample mixture, I had to use glimepiride as a division. So now I'm using metformin as a division. So I have 2 micrograms per ml profile. So this all you have to generate and save there. So I'll just click calculate. So now you give the file. I can give it as a ratio, amplitude difference method, rad 1. Okay. Already exists. I did work it out. Okay. Just say. So this is how. Now you can see the. This is the ratio absorption spectra when you divide the sample mixture of metformin and glimepiride with the metformin as a division, right? Now all this plateau region, in this way I can do for all the concentrations. Now I did for 4 kada. I have started with 2. Anyhow, 4, 6, 8, 10. So that will give you set of data. You can select any one sample concentration. Now, so the next is this is what. So this I can transform to derivative. So just to go the same file I can. The next method is derivative spectrum method. So then I can select transformations. Then see, these are all highlighted. Transformation, derivative, order smoothing. So you can use, and scaling 1 factor is enough for doing. So if I just calculate, then give some file name, derivative ratio. But it is very important. Everything will get saved here. So you should be careful when you save the file, right? Even any missed one, you are unable to, whether it is raw data or already treated data. So file naming is very important to retrieve back the data. Okay. No, this is not the derivative. Okay. Now we can see, calculate. Usually, see, it didn't go to derivative. Okay. We'll go back, calculating. So, then this has to go. It is going back. Well, select any raw data, 10 micrograms. No, we'll leave it. Okay, we'll go for. Now I said no, in the extended ratio subtraction method. So this part you are removing in the plateau region. So this is a constant, right? So just now I'm doing again going back arithmetic. So now you can see this constant I had to remove. theoretically we calculated Cx by C naught m. This I can subtract looking into what is the absorbance here. If we just keep cursor here, you can note down what is the absorbance value of this. So around 0.7. So now I selected arithmetic mean, then I had to select subtraction. Then just this, if I subtract this 0.7 absorbance, 0.7 absorbance, extended subtraction ratio method. So we'll get so this is the normalized derivative mode after doing the subtraction, right? So this is how you can do all the series. So then after subtraction, you'll get a series of overlay methods. Overlay spectra. So by doing the data, by constructing the calibration curve, we can calculate back the unknown concentrations. So now I can say here you are just doing, you are just making use of some manipulations like addition, subtraction, division in such a way that you can eliminate the interference of one component when you are determining the vice versa, right? So this is about some manipulation. So I can say I covered only 20%. You have n number, several manipulation techniques. Every year two or three are added. The scientists will work on it. So the right some new mathematical derivation based on that integration, integrated calculus, then they'll be giving the name of that. They may do that. So I can't say that these are the number of methods which are used for. Okay, so this is all about. Hope I reached you.
Yes, ma'am, that was the wonderful presentation. And I request the audience if you have any questions, queries, so that
Good afternoon, very good.
Let me thank first Santhiram College of Pharmacy and Sivashankar sir for arranging such a nice session which will make us more active after lunch because of
Thanks.
Madam, one small doubt, ma'am, regarding this dual wavelength method. Is there any criteria that we need to maintain the difference between lambda 1 and lambda 2 in dual wavelength method?
You are asking about conventional dual wavelength or induced dual wavelength?
Conventional, madam.
Conventional.
What is the difference between the lambda 1 and lambda 2? Is there any criteria like that?
It depends on the method. If it is simultaneous equation method, the condition is like the absorbance of the two components will show absorbance and absorbance of each other. Like that, absorbance ratio method. It depends on the type of method. The selection of wavelength and wavelength mode will depend on the type of method. It's not uniform for all the technique. Yeah.
The other one, madam, very small note. In isostatic point method you told, na? So in that you have given the formula for 2 drugs actually in the slides. But in the example you have given that 4 drugs estimation. But is there any formula how we can able to do that?
That's what. When it comes to practical, I said no. Everything is did by instrument. You need not worry about that. If you just select the manipulation approach, right? What you have to do there, you are just selecting the 2 wavelengths. You have to do subtraction. You can calculate ratio. That's all that you can design and you do in manipulation approach.
Under the condition also you told, madam, one drug, the X drug should not have any absorbance at the lambda max of Y.
Yeah, then only you can use. Definitely, you have a number of drugs whose spectra is not.
In that case, 4 drugs if we are estimating, so how the condition should be matched?
It's a good doubt, right? No, so then I'll be setting two spectra overlaid for meeting my condition at a time, right? at a time I cannot execute all the four.
Okay,
So I
okay.
can
Oh,
select.
two.
Yeah, so I'll
Okay,
just look into for the defined two spectra
okay.
where I have iso absorption point, then I can go.
Okay, okay. Thank you very much, madam. Very, very nice session.
Yeah, thank you.
Madam, can I
I
what
should
is the
say thank you.
system model? What is the system model which you are
This is
using?
Shimadu
United.
1800, Shimadu 1800.
Okay, ma'am. Thank you, ma'am. Thank you very much. Thank you very much, madam.
Because most of you, we are not aware of that, like we have these many options in the, because we are purchasing the instrument sparing 7 to 8 lakhs, we have to use it A to Z, right? So you have a number of options. You please try to explore and do apply. Thank you.
We do have 1800, ma'am.
Ah, yeah, then Shiv Shankar is going to ring me whenever. Right. Good, good work on that.
We
You are always
tried out to first derivative, ma'am. That we did it. But after we purchased HPLC, then we all shifted to HPLC.
very few, I can say, articles on spectral manipulation methods in national journals, right?
I think
We did lot of theoretical calculations before you work on instrument, right? So that knowledge you need to. Even that you have to work out the calculations and how much concentration you may need for the division or for the subtraction, for multiplication, all that you may need. So that there I forgot to mention. So now I'm dividing and taking ratio, right? So I'm subtracting. Again, if I multiply, then I'll get the raw spectrum, right? If I do back, if I multiply with the concentration of the divisor, I'll be getting back the concentration, right? In that way again. But you need to work on that. Thank you.
any more questions from the audience? You may unmute yourself and kindly. Ma'am, I have one small doubt, ma'am.
Sure.
Ma'am, you have done all this for the assay of the drugs. How far will it be useful for the impurity profiling?
Oh, sure, you can. Yeah, I mentioned in that title which we did. It's for both raw materials and dosage forms. You can apply.
Okay.
Only thing is you have to look into the spectra, how it is, whether it is meeting our condition for multi-component analysis or single component analysis also you can go for. So if you want to increase sensitivity, your spectral characteristics are not good, go for area under curve method, right? So if you expect that the two components are parallelly good with good absorption characteristics, then it's a competition for elimination of the interference. We'll go with it all amplitude ratio methods, subtraction, extended ratio subtraction and all.
Okay. Anybody else want to have a word?
Or anytime you can mail me or you can any kind of right now. So I'm not that good. We started, as I said, 2 years back we started with the area under curve methods. Last year, so we did this manipulation on derivative amplitude.
Ma'am, we just have a lot of thanks and then we'll wind up, ma'am.
Yeah, thank you so much. Yeah, let me thank the principal sir and the management for giving me the opportunity in your eFDP program. So it's from my side a big thanks to Shiv Shankar. So he initiated. So it's good. Thank you very much, and thank you very much for all the audience for the patience listening of this mathematical transformations in the afternoon session post lunch. Thank you.
Now I request Anand Gopal sir to propose a vote of thanks on this occasion. Over to Madam.
Thank you, Santhiram sir. Dr. Y. Padmavati madam has begun with the basics of photometric calculations and later move to entirely new techniques on the spectral manipulations for analysis of drug molecules when in the interfering substances are to be more. We thank Madam for presenting the topic with examples such that the participants can be easily understood for the new research concepts. And we sincerely convey our heartfelt thanks for accepting our invitation for presentation, Madam. We also thank the participants for their active participation for this research conference. Thank you, one and all.
Thank you. Thank you. Good day. Thank you.
Right, ma'am.
Okay,
Thank you very much,
Thank
ma'am.
you, Shiv.
And
Thank
tomorrow, for the participants, we'll begin by 10:30, 10:30 sharp, and we will share the link and the